Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Continuity Lecture 3. So I actually forgot to post the QD 18 and I'll be doing that in the group itself. So let's start with the discussion. So we'll start with the algebra of continuity and this is nothing but recap from limits. So basically we studied one table in limits that let's say limit x approaches a f of x, that is L, and limit x approaches a g of x, that would be m. In that case, if this is true, we can also write limit x approaches a f of x plus g of x, that would be L plus m. And similarly we did this for L multiplied by m divided by m, subtraction, exponential powers, and all those things. We made a particular table, and that same table and with same examples is also applicable for continuity and derivability as well. But there was one case of composite function which was not clear earlier because we didn't study continuity there then. So let me try to explain that one. So that says basically, so the premise stays the same. This is the premise. Limit x approaches a equal f of x equals to L, and this one is also true. Now what we are trying to do over here is limit x approaches a f of gx. That would be equals to f of limit x approaches a gx. Now we can write this only in case of when f of m is continuous. Basically, the function fx is continuous at m. What is m? Limit of gx. So this is nothing but m only. Limit x approaches a, gx is m only. So this is true only in case of this, when this function is continuous at m. Now let's try to prove it. Now in case of LHS, we know that when x approaches a, gx approaches ga, right? And ga is nothing but m. So basically, when x is approaching a, gx is approaching m, right? That is basically true because limit gx x approaching a equals to m. So when x is approaching a, gx approaching m. So I can write this limit as limit gx approaching m, f of gx, same thing, right? And this we know that this is nothing but f of m because this limit is m only. Limit x approaches a, g of x equals to m. So this is nothing but f of m. Now we have this condition. If these two want to be equal, if these two have to be equal, in that case the function fx should be continuous at m. Now try to look at this one, these two expressions. So this is nothing but f of this is nothing but limit x approaches a, fx equals to f of a, right? So x is approaching a here, gx is approaching m, and that is f of m. This is f of gx approaching m, right? Same thing. So this is the definition of continuity, right? So that proves our point. If these two has to be equal, the function f should be continuous at m. Now let's look at more practical theorem, that is intermediate value theorem. So let me draw one diagram first. So let's say this is our point A, this is point B, and let's say these are 2 points. This is FA and this is FB, right? Now we have got 1 point over here. We have got 1 point over here. Now if f is continuous on A to B, both close brackets, and fa not equals to fb, we have maintained that, then for any value c that belongs to fa comma fb, open bracket, basically the value c is not equals to fa or fb either, there's at least one number x in a to b for which fx equals to c. So basically, let's say we have taken one value c over here, right? Now it says that for any value c in between these two values, it will definitely take one value of x that is in between a to b. Now how to prove it? Now we know that f is continuous. So basically we don't have to lift our pen. So it can be maybe in this manner or it can be simple straight line. Anything is possible. Now this value is like this. So I can see that For this upper function, it's going to cut over here. For this lower function, it's going to cut over here. And it might even cut at multiple points. Let's say the function is like this. It's cutting at 1, 2, 3 points, right? So we can clearly see that there is at least one number x in the range a to b, where this value f of that number, let's say that number is x naught, f of x naught would be c, right? Got the point? So that is a very intuitive derivation. Now the more practically used in examinations is intermediate value alternative version. So what this says is, so we have, let's say we have, this is a value, this is b value over here. Now it says that this value is negative fa, and let's say this value is positive. It can be vice versa too. Fb can be positive, if fb can be negative, fa can be positive, both ways. Let's take one example. So over here fa is negative, fb is positive, right? So this is fb and this is fa. Now if I do the same thing over here, if I draw one function from a to b, a continuous function from a to b, I can clearly see that it is definitely going to cut the y equals to 0 line, basically the x-axis, at some point in between a and b, right? I can make the function like this, I can make the function like this, but it's definitely going to cut this function, basically cut x-axis. So cutting x-axis means one root, right? And that root is lying in between a comma b. So if the alternate version says that if fa dot fb is less than 0, in that case it's definitely going to have one particular root in between a to b, right? At least one root. It can go like this over here. It will have 3 roots over here, so at least one root. Now how to identify that? We have to use these kind of theorems in questions. So this will be the keyword, at least one root, at least one value. So whenever you find these kind of keywords in continuity questions, then probably you have to use intermediate value theorem. Now let's look at one example. Using intermediate value theorem, prove that there exists a number x such that x raised to power 2005 plus 1 divided by 1 plus sine square x equals to 2005. Now we know that this is a polynomial function. X raised to power 2005 is a polynomial function, so that is continuous. And this is a rational function in terms of trigonometric function. So 1 upon sine square, 1 plus sine square x, that is also always positive. So basically denominator is always positive. So hence our rational function is always continuous. Continuous function plus continuous function is always going to be continuous, right? So we have proved that fx equals to x raised to power 2005 plus 1 upon 1 plus sine square x is a continuous function. That one thing is there. Now it has to take one value 2005. So basically we have to find a range that contains 2005. So one obvious point would be a point which is greater than 2005 and a point which is lesser than 2005. So lesser than is clearly f of 0. So basically f of 0 is nothing but 1. 0 plus 1, that would be 1 only. Now if I try to find f of 1, in that case I can clearly see that this is again not greater than 2005. It's again less than 2005. So basically what I'll do, I'll write f of 2 over here. So that would be 2 raised to power 2005 plus some value, some constant value, let's say c, right? So basically we got the point that this is greater than 2005. So we have got 2 points, 0 comma 2. This is the range. Now this is our 0 point. At 0 the function value is 1. At point 2 the function value is 2 raised to power 2005. Let's say f of 2. Let's call it as f of 2 only, right? So this is the point over here, this is the point over here, and let's say the function is something of this sort, exponential, because this function is kind of exponential, right? Kind of exponential, not exactly exponential, right? Now I can clearly see that this is some value 2005 over here, and this is definitely going to intersect at some point, and that point would probably between 1 and 2, because we also know that 1 is also f of 1 is also lesser than 2005. So to be more precise, the value would be in between 1 and 2. Now let's look at this illustration. There is at least one root of fx equals to cos x minus x square in 0 to pi, true or false. So let's check it out. So when we're talking about at least one root, then we have to find that f of 0 dot f of pi should be less than 0. That would suffice the equation. Uh, that would suffice the condition actually, right? Cos x is continuous, x square is continuous, though, so the summation or subtraction is always continuous. So we know that fx is continuous function. Now f of 0 would be cos 0, that is 1, minus 0 square, that would be 0. So f of 0 is 1. F of pi, that would be cos pi is minus 1, and that would be minus pi square. So that will become minus of 1 plus pi square, right? Now you can clearly see that f of pi is negative, f of 0 is positive. So f of 0 dot f of pi is less than 0. So according to our alternate version of intermediate value theorem, we can clearly see that this has at least one root in this range. Now the important point is, after learning all these concepts, how should one judge that okay, on these points we have to consider the checking of discontinuity or continuity, right? So we should have one framework so that we can get to know the points on which we have to check the function's continuity or discontinuity. So let's have that framework. The first one is functions in interval should be checked at points where definition of the function changes. So let's take an example first. Let's say our function is defined like this: 1 plus x square and 1 minus x square, and that is defined like, let's say this is minus 1, and this is less than 1 greater than equals to minus 1, and this is less greater than 1 equals to 1 and less than infinity. So let's say a function is being defined like this in three parts. Now I can clearly say that at this point, at minus 1, the function definition is changing from infinity. So sorry, from minus infinity to minus 1, it's constant. So it's a polynomial function. It's going to be continuous, but the function definition is changing at x equals to minus 1. So we have to check at this point, right? Now at this point, this is the point over here, x equals to 1. Again, the definition of function is changing. So again, we can say that this function was continuous in this range. This function was continuous in this range, but at this point, this definition is changing. So we have to check it this point. So this is our first way to identify the points. The second one is polynomial, rational, trigonometric, exponential, logarithmic, inverse trigonometric functions are continuous in their domains. So what do we mean by that? Let's say we have a function fx equals to tan x. We know that at odd multiples of pi by 2, this is minus pi by 2 and this is pi by 2, the function tan x is discontinuous. So basically it's not defined over there. But can we say that this point is in its domain? So this point is not in its domain because it's not defined over there. So its domain is for this diagram, for this graph, its domain is minus pi by 2 to pi by 2. And it's continuous over there. You can clearly see that at x equals to pi by 2 and x equals to minus pi by 2, we can say that it's not being defined over here and hence discontinuous. So unless deliberately asked, you can easily say that these functions, trigonometric functions, inverse trigonometric functions, polynomials, modulus, all these functions are continuous in their domains. So, but let's say we have been asked in the question, check the continuity of this function tan x in the range 0 to pi. Now you have to mention this point pi by 2 as a point, as a discontinuity point. Now the third point is fractional part function, greatest integer function should be checked at all those points where the function becomes integer. Now this one is primarily used for continuity checking. The earlier examples were very basic and very intuitive, but these are not very intuitive. GI functions and fractional part functions and mistakes can be made over here. Let's say we have a function fx equals to GI of fx square and maybe GIF of root x. Now over here, this internal function will become integer at x equals to 1, root 2, root 3, 2, root 5, and so on, right? So you have to check at these points too. So one might miss out on these points by directly checking at 1, 2, 3, and 4 and all these points, but you'll have to consider these points as well, root 2, root 3, root 5. So that can be a trick question over here. Similarly, for this one, it can be 1, 4, 9, 16, that way, right? So because you cannot have two value over here, so you'll have to check at 4, 9, basically integral points. So the internal part function, this anything inside this function is becoming integer, you have to check at that point. Let's say we have a composite function like this. Let's say mod x minus x square, and this inside GIF function. Now you have to check for these points, where these points are becoming integral values, where this function is taking integral values. So you have to check at those points. Now let's take the example of continuity of composite functions. Let's say we want to calculate f of gx, and we have to check the continuity of f of gx. So it will have two parts. The first one is we have to first check the continuity of gx itself, because at x equals to, we are going to consider the points of domain of gx, right? So in this case, x equals to 2 is one point. X equals to 2 is one point where this function gx is not going to be continuous. So this is not going to be in domain of the entire function. So it's not going to be in the domain of gx, and hence it's not going to be in the domain of f of gx, right? So the first point of discontinuity would be this one. Now the second one would be, let's write f of gx. That would be gx plus 1 divided by gx minus 1. I can clearly see that this would be the second point where the function is not going to be continuous. So at gx equals to 1, it would give us 1 point where the function is not going to be continuous. So this and this point. So let's try to do it. Gx is what? 1 upon x minus 2. That would be 1. That would give me x equals to 3. So at x equals to 3 and at x equals to 2, these 2 points will give us the points of discontinuity of this composite function. Now let's write g of fx over here. Now what we'll do, we'll look at the domain of fx. So at x equals to 1, we can clearly see that fx is not defined, so basically discontinuous. So this is going to give us 1 point. And also when I'm going to write 1 upon f of x minus 2, basically g of fx, basically I'm writing this as g of fx 1 upon fx minus 2. So fx equals 2, that would give me one more point in addition to this one for this function to be discontinuous, right? Now let's look at one last miscellaneous example of continuity, and that would wrap up the entire series of continuity chapter. These questions might not be asked, but they are important from the concept point of view. First of all, treat this as x raised power n. A raised power n might confuse you, so treat this as limit n approaches infinity x raised power n. Now, when we know that n is some finite value, in that case, x raised power n can be plotted just normally. But when n approaches infinity, then we know that the base value matters a lot. So we'll have to break down this function into 3 parts. So when x equals to 1, x greater than 1, x less than 1, right? For x less than 1, and obviously greater than 0 because it cannot be 0, right? For x greater than 0, less than 1, that would be 0, nothing but 0. In that case, in case x is greater than 1, anything 1 plus h raised power infinity, that would close to be, not h, but maybe let's say 1.5 raised power infinity, that would be close to infinity. So that would be infinity over here. And anything of exact 1, raised power exact 1, that would be 1 only. So we have divided this function into 3 parts: x greater than 1, x equals to 1, and x less than 1, greater than 0. Now, since the definition of function is clear, we can definitely check the continuity of function, and we can clearly say that LH and RHL are not equal, and they both are 2 different values, and also f of 1 is also different from both the values. So this function is discontinuous at x equals to 1. You can also get functions like limit n approaches infinity, f of x equals to, and that would be x is power n minus 1 divided by x is power n plus 1, and maybe vice versa, opposite one, x is power plus 1 in the numerator and x is power n minus 1 in the denominator. So again, you'll have to mark down these cases for different values of x, for different values of bases basically, and after that you can start solving the question, basically checking the continuity of the question, of the function. So today's lecture was till here only, and from tomorrow onwards we'll be starting with the differentiability, and after that we'll start with the methods of differentiation. And we're not able to solve too many questions during the lessons because of the time constraints. So if you want to solve more questions, you can join the Prep Master program. You'll get many quizzes and examples over there. So let's meet tomorrow for the differentiability lecture 1, and thanks for watching.